Alright, in this video we will be going over the circuits review practice here. Alright, last series, as resistors are added in series, what happens? So that's if I have, say, a circuit with one resistor, then how does that compare to a circuit with two resistors, and so on. So we can say with three maybe. And I'm looking at how the current and so on changes. Alright, so the current through each resistor. I know in a series circuit that the current going through the circuit is the same for all things in the circuit. So I want to compare this current to this one to this one. What's happening to that current as I add more resistors here? And I know, based on my series rule, as I add these in series, the overall resistance of the circuit goes up. So overall, I could say, this first one has a resistance of just R. This one has a resistance of 2R. This one has a resistance of 3R. And I know from Ohm's law that if I'm keeping the battery the same, it's the same V, and my overall resistance is increasing, then my current is going to need to go down, because more R means less I for the same V. So each of these resistors are getting less current than this resistor. They're actually going to be getting half as much current, because there's twice as much overall resistance and they all get the full current. The current outputted by the battery, well, same reason. It's they all the same current, and that current we just talked about is going down, so the battery's putting out less current. The potential difference across each resistor. So let's look at that here. So in my case of the one resistor, that resistor is changing the potential by the full amount. If we look at this guy here, it's changing it from the blue to the red. When I have two resistors, this is not changing the full amount. It's changing it part way, and then the other one does the rest. Three resistors, they're each changing even less than that. So I know that the potential difference across each resistor is decreasing. So if I look at this resistor here, it's not changing it as much. These are different purple values. It's not changing it as much. Here it's changing it full V. Here it's changing it half of V. Here it'll be changing it a third of V. So that's going to decrease. The power outputted by the battery, well, P equals I delta V. Same V. We talked already, I have less I, so I'm going to get less power. And you can always associate power with current. If I have the same object, the less current, it's going to have less power. So same deal for these resistors. This resistor had more current compared to these. So this resistor had more power compared to, say, the power from this one with less current. So because their current went down, their power drainage dissipation went down as well. Okay, now we're adding in parallel. So now we've got, can start with our basic circuit. Now I'm adding another path, basically. I'm adding another way for the electrons to travel. That's how we should always think about parallel. All right, the current through each resistor. So again, let's think about equivalent resistance. This would have R. If I did the math, this would have resistance R over 2, because 1 over R plus 1 over R is 2 over R, and then I flip it. This would have R over 3 for an equivalent resistance. So I can see my overall resistance in my circuit is actually decreasing as I add more resistors. And that might seem counterintuitive, but remember, when I'm adding these resistors, I'm adding them as an additional path. So I'm actually giving more ways for the current to flow. So overall, less resistance. So current through each resistor. It's going to require a little color coding. So my overall current is going to increase because my overall resistance decreased. But if we're talking about just the current through one resistor, that's going to be a little bit different. So I can see here, my resistor, it's changing it from whatever the battery is putting out to 0. And it has a certain resistance, which would give it a certain current from Ohm's law, delta V equals IR. So I can see that this current is based on the delta V and the R. If I look at one of these resistors, it has the same delta V. It's doing the full battery voltage. And this resistor has the same, this is R, this is R, this is R, and so on. So this resistor here, if we look at what it's doing the same thing as the resistor in the simple circuit. And this one's doing the same thing as the resistor in the simple circuit. So it must have the same current in order to do that. So the current going through this resistor, whatever that is the same as the current going through this one, is the same as this one, same as this, same as this, same as this. These are all the same currents because these resistors have the same resistance and are doing the same delta V. So Ohm's law tells us same current. So the current through each resistor stays the same. And you can think about that. This is just this loop, if the electrons are going like this, is exactly like them going like this. Them taking this path looks exactly like if there was just that path. Here I just have 3 iterations of that same shape, same path. Now the battery, on the other hand, if I look at where these currents come together, the battery here has to be putting out twice as much. We call this I, and these all have I. The battery here has to be putting out 2I because it's providing I here and it's providing I here. So overall, it's providing twice as much I. And we carry these back. This battery is providing 3 times of that because it's providing this I, and this I. So overall, it's providing 3I. So as I add these resistors in parallel, my battery has to actually put out more current. Potential difference across each resistor, we saw from our original explanation that each resistor is getting the full voltage of the battery, and that stays the same even as I add more because I'm just adding more paths off of the battery. Because the battery is outputting more current, we know P equals I delta V. More current means more power. You can always relate those two directly. Power dissipated by each resistor. Well, we said that each resistor has the same current, which means same power. Again, we can just relate power directly to current. All right, here we're just doing our standard sort of situation. We have the battery voltage, we have each resistor, and we're just figuring everything out about the circuit. So let's do that. Let's label what we know, figure out how we can get what we don't know. We've got a main current going like this through the battery, and then it's splitting up into these 2 paths. We've got a 20 ohm, a 5 ohm, 13 ohm, and a 7 ohm. These are my resistors. I got my battery, doesn't have a resistance. I don't know any currents just yet. We want no power, so we'll add a column for that. Oops. Okay. It's a 90-volt battery. And that's it. That's all we know. So we know in a situation like this where I know all the resistors and I know the battery, I can find the total current, which would be this current going through the battery and the 5 ohm resistor here. They're on the same line, by finding the equivalent resistance of this circuit. So I'm going to start combining things. Let's see, these two are in series, same current going through them, so they're in series. 13 plus 7, I can treat those as a 20 ohm resistor. So I have this one, oops, forgot my 5. And now I have another 20. And I can see if I looked at these, that they are now in parallel. So I'm going to do 1 over 20 plus 1 over 20. Or I could just say, oh, I know when I have two of the same resistor in parallel, I get half the resistance. But this math will work out to that. I'll get 2 over 20. So now I have 10 and 5. So that's 15 when I put those together. We'll draw it. Because they are in series, same current. So I have 15 ohms, 90 volts. That gives me a current using Ohm's law, delta V equals IR. This resistor's changing it by 90. 90 equals I times 15, then I has to be 90 over 15 is 6 amps. Okay, so I'm going to go back to my thing. I'm going to label, I have 6 amps as my total current there. How does that help? Well, that's 6 amps. I draw the full line as going through the 5 ohm resistor. Just getting 6 amps. I can find its delta V, 30 volts. So if I look at my picture here, I just found this was 30 volts, so I'm going to look at that and I'm going to say 0, this side then has to be 30 volts because now there's a change of 30 over this resistor. Okay, just found out this is 30 volts. How does that help me? Well, let's see. Well, I still don't know this purple bit, but I know the blue is 90. So I have 90. This is changing 30. Another way to think about this is if I go around, I have to get back to 0. So 90, change of something, change of 30, I need to be at 0. So this change needs to be 60. Or I could just say 90 and 30, well, that's a change of 60. So the 20 ohm resistor here has to be changing it by 60 volts, because if I take any loop, I need to get back to 0. 90, lose 60, lose 30, I'm at 0. So that means I can find what this current is. 60 divided by 20 is 3 amps. All right. So let's label that 3 amps. And now I can say, well, 6 going in, 3 going this way. Current needs to be conserved, because charge is conserved. 6 splits into 3. This must also be 3 amps. I could also find out, I could also look at this and say, well, these are the same deal, so they need to have the same current when I combine these two. So I got 3 amps, and these are both getting 3 amps. They're getting the same current, no splits or anything. One unbroken line until it comes back together to make 6 again. Okay, so 13 times 3 is 39 volts, and 7 times 3 is 21 volts. And I should check, I know as it goes over both of these, it changes by 60. It's going from the blue to the orange. And 39 plus 21 is in fact 60, so we are good. The battery had a 6 amps coming out. Now it's just doing a bunch of math to find the power. Power is I delta V. So we've got 180 watts. Another 180 watts. And 3 times 39 is 117. 3 times 21 is 63 watts. 6 times 9 is 54, 540 watts. And if we add all these together, all the resistors together, we will find that it equals the battery's power. So the battery puts out 540, these drain 540. Energy is conserved. It's always a good thing to do to check your work. All right, determine the voltage of the battery. Now in a situation like this, I would maybe think about, can I combine resistors? I only need to know the voltage. I don't need to know anything about the other resistors, so maybe I try to put them together. The problem I run into on this question is I can't combine this 20 with anything, because then I lose this information I was given. I lose this information that I have a current of 0.25 only going through this 20. I guess you could put the 4 and 5 here together if you wanted to. I'm not going to, but you could definitely do that. All right, so we've got 3 loops. They all involve going over the 8 ohm, and then it goes over one of these. So these are all in parallel. So you have the main current, which is going through that battery and that 8 ohm, and then it's splitting up and going down these 3 ways. And I want to know the delta V. So to do that, I need to find out exactly how much the voltage is changing after going around one of these loops, and that'll tell me what the battery voltage is. So I know the voltage going, I can find that because I know the current in this. So I need to find the delta V of this 8 ohm, which means I need to know what this current is here. So that's going to be my goal. I can find this total current here. I can find this. To find that total current, I can see, and okay, I know one of the currents. If I can figure out these other 2 currents, I know these 3 added together have to be this total current here. So let's try to make that happen. Let's make a table just to stay organized. 8, 4, 5, 20. R, I, delta V. Battery, we don't know. So, all right, so we know 0.25 amps through the 20. So 20 times a quarter. That's going to be, what, 5? Yeah, 5 volts. Okay, so see if that helps me. I know this is 0. I know this is changing by 5, so I need to have 5 volts up here. And hey, these are in parallel. So I know this is 5 and this is a change of 5. They're all changing it by the same amount. So 5 volts, 5 volts. And now I can find their currents because I know their delta V's and their R's. 5 divided by 5, 1 amp. 5 divided by 4 is 1.25 amps, 5/4. Great. Why did I want those? Well, 1.25 and 1. So we've got a current, and it's splitting into these three. So these three added together get me back to my main. Another way to look at it is if I follow these around, they all come back together to make this. So this needs to be 1.25 plus 1 plus 0.25. That ends up being 2.5 amps. And that's what the battery's getting, and that's what this resistor here gets as well. Which means it has a delta V of 8 times 2.5 is 20 volts. If we wanted to check and make sure all this information is correct, again, we could, we want to include the battery. Battery's getting the full 2.5 amps. I guess we gotta find the voltage of the battery before we can check by finding power. All right, so I'm an electron. I'm going around one of these loops. I change by 5 volts, and then I change by 20 volts, which means that's an overall change of 25. Say I go around this loop, I go over the 8 and the 4, which means my battery needs to be putting out 25 to conserve energy. Should work for any loop. So let's say I go over the 5 and the 8. Well, the 5 and the 8, 25. Let's say I go over the 20 and the 8. 20 and 8, 25. Batteries putting out 25 volts, 25 joules per coulomb. And send the written solutions if you want to check the power outputs. But we end up with 25 volts. Okay. Determine the value of the unknown resistor. This circuit below. So in this case, I don't want to combine everything, or maybe I could. There's a way I could do that, but I think it's easier to just go through step by step and figure everything out. So I've got this 2 amps. We'll do it both ways. And then that 2 amps is splitting into these 2 currents here. All right. So immediately I can say, I know this current, I know these resistors, I can find these changes. This is a change of 2 times 37. And you could do this in your table if you wanted. It's 74 volts. This is a change of 2 times 10. Oops, I messed up. This is not 74, that's the change. The change is 70, easy mistake to make. The change is 74. Because I didn't write this down. I should have written, this is 100. 100 minus 74 is 26 volts. All right, let's not make that mistake again. This is 0 volts. The change is 2 amps times 10 is 20. So this is 20 volts. All right, so I know this change is 6, but I still don't know what this current is. But I know this change is 6. So 4 ohms changing by 6, 6 divided by 4 is 1.5. So I found 26, I found 20, that tells me the change. From that change, I can get this current. Now I need to know this current to find this resistor. This is 1.5, this is 2. So I have 2 going in, 1.5 goes this way. That means 0.5 needs to go the other way to conserve current. Great. So now I say delta V equals IR. My delta V is 6. My current is 0.5. So R has to be 12 ohms. And again, if I made a table, I can find the power for everything. Check my work. I would find that the power from all the resistors equals the power from the battery. Other way to do it, using equivalent resistance. So let's say I colored this. I can combine these. 1/4 plus 1/R. Now this way I maybe don't do because the math is weird. Equals 1/REQ. So yeah, we're not going to do it this way. This is a lot of algebra. But you could do it that way. You're given a 3-volt battery and you want to come up with a bunch of different ways and find the power. All right, well, the easiest ones to think about, straight up series circuit, 3 volts, 1 ohm each. Determine the power from the battery, so we need to know the current. This current, these 1 ohms I can treat as a resistor of 3 ohms because series rule I can add them up. Gives me a current of 1 amp because 3 volts divided by 3 ohms. And then P equals IV. So my power is 30 watts for this one. Next easiest one to think about in my mind is, okay, I'm just going to put them all in parallel. So 1, 1, 1, and 3. All right, I know in parallel, if I add these, that's 1/1 plus 1/1 plus 1/1, which is 3, and then reverse that, I get 1/1 plus 1/1. All right, I get 3, which means I get a resistance of 1/3. So this is like having this, where this is 1/3 ohms, which means I get a current of 3 divided by 1/3, which is 9 amps. Another way to do that is to say, well, this is 1 ohm. It's a change of 3 volts. If I look at its delta V, it's taking it, it's going straight from the battery. So these are each changing it by 3 volts, which means the current through here is 3, through here and here are all 3. So they have to add up 9. 9 out gives me 3 down each path. All right, and then again, I can use power equals 9 amps, 3 volts for the battery, 27 watts. All right, now we got to get a little bit tricky. So I can't do all series and all parallel. Oops. So I'm going to do 2 in parallel and 1 in a series with those. 1 ohm, 1 ohm, 1 ohm, 3 volts. Again, we're looking for the current from the battery, so I'm going to combine these resistors. The 2 in parallel become 1/2 an ohm. Because 1/1 plus 1/1 is 2/1. Flip it, you get a half. I combine those. That's 1.5 ohms, which gives me a current 3 divided by 1.5 is 2. So power from the battery is 2 amps, 3 volts, 6 watts. How many do we need to do? 4 different circuits. We've done 3 different circuits. Let's see, we did all parallel, all series. What if we did a... Here you just sort of play around if you find something that's different from what you did already. These two are in series, but they're in parallel with this other one. All right, so 3 volts, 1 ohm, 1 ohm, 1 ohm. Let's stick all these resistors together. So these two are in series, so that's 2. And then I have 1 over 2 plus 1 over 1 is 3 halves. I flip it to 2/3. So that's going to be a little bit weirder of a number. 3 volts, 2/3 ohms gives a current. 3 divided by 2/3 is 9 halves. 9 halves amps. So 4.5. So power equals 3 volts, 9 halves amps is 13.5 watts, because I get 27 over 2. And that's it. All right, cool beans.